Hello students, welcome to second video on some special distributions. So last class we have discussed about normal distribution. Today we are going to discuss Laplace distribution as well as Poisson distribution. Two distributions will be same. So the objective we have to revise what we have studied in the last class, and you have to see the probability density function, cumulative distribution functions for Laplace distribution, and also problems on Laplace distribution. Similarly, we have to see the probability mass function because Poisson is a discrete random variable and its cumulative distribution function, mean and variance. Also, we will work out some problems on Poisson distribution. So, revising, last class we have studied a normal distribution whose density function is given by fx of x is equal to 1 by root 2 pi sigma e raised to minus x minus mu whole square divided by 2 sigma square. And in order to solve the problems, we have to find the CDF. So instead of CDF, we have phi of z. The phi of z is given by 1 by root 2 pi minus infinity to z e raised to minus x square or any variable tau squared by 2 d tau. And one more important property, phi of minus z is equal to 1 minus phi of z. So in the last class what I missed out is explaining this part. So we know phi of z is integral. So the phi of z integral comes from this minus infinity to z. So that is why phi of z. So that will be the area, this portion, area under this graph. Now this is for the positive z. Now when it comes for the negative z, the area under the graph will be this portion, minus z. Now the table has only positive values as I have discussed in the last class. So we won't get value for negative z. But in the graph, if you can see, this portion is same as this area, because both are the graph is symmetric, so this area will be equal to this area. Now what is this area is actually total area minus area up to this point. So if this is minus z, this will be plus z. Now phi of plus z will be the area from minus infinity to this portion, this area. So phi of minus z, this area will be 1 minus phi of z. So that is why phi of minus z is equal to 1 minus phi of z. Now moving into today's distributions, the first one is Laplace distribution. So Laplace distribution, the random variable x is called Laplace random variable if its probability density function is given by fx of x is equal to 1 by 2 sigma e to the power minus mod x minus mu divided by sigma. Now the function is somewhat similar to our normal distribution, but the thing is, here it was root 2 pi, now it is 2, and here it was x minus mu whole square by 2 sigma square. Now here it is minus x minus mu divided by sigma. So this mu is the shifting factor and sigma is called the scaling factor, and 1 by 2 sigma is the amplitude of the probability density function. Now this is a mod function, so we know that if it is mod, the f of x will be minus x when x is negative and plus x when x is positive. Now instead of x we have x minus mu, so x minus mu is negative and x minus mu positive means x less than mu as well as x greater than mu. So the function is piecewise like this, when x less than mu as well as x greater than or equal to mu. When x less than mu, minus of x minus mod x minus mu will be minus of x minus mod x minus mu will be minus of x minus mu. So minus minus cancels, it will be x minus mu divided by sigma. And when x greater than mu, it will be positive. X greater than mu, x minus mu will be negative. So it indicates minus uh, minus of x minus mu. So minus x minus mu can be written as mu minus x. So we have the function is defined from minus infinity to mu, and after mu to infinity. So the graph will be symmetric about mu. Now we will see what is the difference between this Laplace distribution as well as Gaussian distribution. If 0 here, otherwise it will be mu. The Gaussian distribution curve is smooth around the mu, whereas Laplace distribution has a steep decrease. So this is one part of this graph is actually exponential distribution. So another side also it is having exponential distribution will having only one side, whereas Laplace distribution has both sides. That is why it's also called double exponential distribution. The Laplace distribution used in biological process, finance, economics, and signal processing applications, and also financial engineering like credit and exotic options, insurance claims. In those cases and all, Laplace distribution is used. Now moving to the cumulative distribution function for Laplace distribution, we know that fx of x is equal to minus infinity to x fx of x dx, where small fx is the probability density function. So it will be minus infinity to x 1 by 2 sigma e raised to, instead of using x confusing with this x, I am using another variable called alpha minus mu divided by sigma d alpha. Now as we know, mode function is piecewise between from up to mu and after mu. So I can find the values in two different cases. When alpha is less than mu, it will be minus infinity to x 1 by 2 sigma e raised to alpha minus mu by sigma d alpha, and integrating and substituting the value, it will be 1 by 2, because e raised to integral of e raised to alpha minus mu by sigma will be e raised to alpha minus mu by sigma divided by 1 by sigma. So sigma here and sigma here cancels, so 1 by 2 e raised to x minus mu by sigma. Now when alpha greater than mu, we have same expression, but when it comes to here, the alpha goes negative, so its coefficient will be minus 1 by sigma. So the entire expression will change to minus 1 by 2 e raised to mu minus x by sigma. Hence we can conclude that fx of x will be half e raised to x minus mu by sigma when x is less than mu, and minus half e raised to mu minus x by sigma when x is greater than mu. And the mean and variance of this one will be, mean will be mu and variance will be 2 sigma square, whose derivation is out of scope of our syllabus, so we are not discussing about that one here. So we'll discuss a problem on Laplace distribution, given that suppose that the return of a certain stock has a Laplace distribution with mu equal to 5 and sigma equal to 2. Compute the probability that the stock will have to return between 6 and 10. So we have to find the probability of x getting between 6 and 10, that is probability of 6 lesser than or equal to x lesser than or equal to 10. We can solve this problem in two methods. The first method is where we have to integrate from 6 to 10. 1 by 2 fx of x dx, so that will be 1 by 2 sigma e raised to minus x minus mu by sigma dx. So substituting and integrating, you will get the value 0.26. The method 2 is we know that probability of a less than x less than b will be fx of b minus fx of a. So using that, fx of 10 minus fx of 6. Here 10 and 6 both are greater than mu, so I have to use the second function in the fx table. So that will be fx of minus 1 by 2 e to the power mu minus x by sigma. So substituting the same, I will get the same value 0. So this is about Laplace distribution. So it was simple. Now moving to the Poisson's distribution. So about probability mass function of Poisson distribution. A random variable x is called Poisson random variable if its probability density probability mass function is given by fx of x is equal to e raised to minus lambda into lambda to the power x divided by x factorial, where x takes the value 0, 1, 2, etc. So x is not taking all the values, hence it shows that this function is a discrete random variable, and whatever things we are using here will be summation instead of integration. So it is like it is defined only for integers, x as integers. So the main important thing is it is an approximation of binomial distribution. You know, Bernoulli distribution is used when you have only two probabilities, p and 1 minus p. When number of experiments are more, it will be n and p. So that is a binomial random variable. When n is very large, when n tends to infinity and p is very small, the probability of success is very small, then a large value into a small value will be a constant or moderate size like 2, 4, 5, like that. So that is called lambda. So that parameter, using that parameter, this distribution is defined. So the applications of this one is like most of the cases it is measuring the time remaining for in the queue. So it is used in queuing process, like in a computer the programs are queued, or somewhere somebody customers are entering and queue, staying in the queue. So what will be the remaining time, like that if you want to calculate. So and more related to queue, we are discussing about Poisson distribution. So some of the examples are the number of telephone calls, the number of misprints on page of a book, number of customers entering a bank during various intervals of time. So all those things can be calculated using, or can be modeled using Poisson's distribution. So we have to find the CDF. CDF is simple. Fx of x is equal to, since e raised to minus lambda is not containing any x term, so we have to only summate k equal to from 0 to x lambda raised to k divided by k factorial. Instead of x here I am using k because x is used here. So the graph for lambda is equal to 3 is shown like this one. When lambda value of lambda is 3, this will be the graph, and for different lambda the graph shape will be different, and it is capital Fx of x, the cumulative distribution function. Since this is discrete, it is having a stem plot, and since this is discrete, it is like added up, it's like a piecewise constant values. Now we will derive expression for mean of Poisson distribution. So we know that expectation of x is summation x is equal to minus infinity to infinity x fx of x. Now our function fx of x is defined from 0 to infinity only, so we can change the summation x is equal to 0 to infinity instead of minus infinity to infinity. Now fx of x is e raised to minus lambda raised to x into x factorial into x minus 1 x factorial. Now when x is equal to 0, this entire term becomes 0, so that term is 0. The remaining sum are x is equal to 1 to infinity. Now x cancels with x factorial, so x factorial is actually x into x minus 1 into x minus 2 into x minus 3 etc. up to 0, up to 1. So when x cancels here, remaining term is x minus 1 factorial only. So e raised to minus lambda raised to x minus 1 factorial. Now in this one, e raised to minus lambda is a constant which we can take it outside. Now denominator is x minus 1 factorial. Let us make the power of lambda also same. So lambda raised to x is there, take lambda outside, so you have lambda raised to x minus 1 divided by x minus 1 factorial. Now we will expand this summation. When x is equal to 1, it will be lambda raised to 0 divided by 0 factor, that will be 1. X is equal to 1, 2, it will be lambda raised to 1 divided by 1 factorial, like that, lambda square by 2 factorial, lambda cube by 3 factorial, etc. up to infinity. Now this infinite sum is actually e raised to a lambda. So e raised to x is expanded as 1 plus x by 1 factor plus x square by 2 factorial, etc. like that. So this infinite sum is e raised to x, e raised to lambda. Substitute that value here. So you will get lambda e raised to minus lambda into e raised to lambda. So this into this will be 1. So the final value will be lambda into 1 equal to lambda. Now finding the variance takes a similar way, but since the x square term is there, we cannot cancel with the factorial term. So what we have to do is x square should be decomposed as x into x minus 1 plus x. So expectation of x square will be expectation of this term plus expectation of this term. So if you find the first term here, that will be expectation of x into x minus 1, as we did in the same way. It cancels at 0, it will be 0 when x is equal to 0 as well as x is equal to 1 in both cases. So 0 plus, so the summation starts from 2 to infinity. E raised to minus lambda, lambda raised to x, and x cancels with the x factorial, remaining is x minus 1 factorial. X minus 1 again cancels, so remaining is x minus 2 factorial. Now you can take e raised to minus lambda. To make same value here, we have to take lambda square outside, so that will be lambda raised to x minus 2 divided by x minus 2 factorial. Now substitute the value of x, it will be the expansion of e raised to lambda. So substituting that, you will get the value lambda square. So e of x square will be e of x into x minus 1 plus e of x. So e of that we got lambda square plus e of x will be lambda. Now variance will be e of x square minus e of x whole square. So lambda square plus lambda minus e of x is lambda, so lambda square, which cancels lambda. So the important thing to remember is that the variance as well as mean both are lambda for a Poisson distribution. See a problem: the number of telephone calls arriving at a switchboard during any 10-minute period is known to be Poisson random variable with the lambda is equal to 2. As we discussed, it will be used when you have waiting periods like this. So find the probability that more than 3 calls will arrive during any 10-minute period. So what we have to find is the probability that more than 3 calls, for probability of x greater than 3. So lambda is equal to 2, x is number of phone calls, so we have to find probability of x greater than 3. So that will be 1 minus probability of x less than minus 3, less than or equal to 3. The problem is that probability of x greater than 3 we cannot find, because directly cannot find, because 3, 4, 5 up to infinity we have to add. Instead this will be added from 0 to 3. Now that will be 1 minus x is equal to 0 to 3 is the expression. Substitute lambda is equal to 2 and expand the summation from 0 to 3, you will get like this. Substitute lambda is equal to 2, it will be 1 plus 2 plus 4 by 2 plus 8 by 6, and multiply with e raised to minus 2 and subtract from 1 minus 2, you will get the value 0.1143. Second part of the question is find the probability that no calls will arrive during any minute. So we have to find the probability of no calls. X is equal to 0. So probability of x is equal to 0. Directly we can find x, substitute x is equal to 0 in the expression of Poisson distribution. So the fx of 0 e raised to minus lambda, lambda raised to 0 divided by 0 factorial. Lambda raised to 0 will be 1, 0 factorial is 1, so e raised to minus lambda only, so e raised to minus 2, 0.135. So this is about Laplace and Poisson distributions. Please note down the things, and also make a note of all those things in your notebook. We will see the conditional probability distributions in our next video, that is on Wednesday.